In another video, last time we talked about the importance of material behavior or material response in determining the structural response and doing the structural design. And those of you who may not have watched that video, please search for material response. But today we are going to go one step ahead, and we are going to see how the cross-section of a member affects the structural response, because this is the second level in terms of the structural hierarchy or the structural system hierarchy, because the structures are made from materials, and then from materials cross-sections to members, and members to elements, and so on. So now we are looking at the cross-section of a typical structural member. And when we say structural member, it could be, we are talking about a member which is primarily a one-dimensional, for example, like a beam or a column or a truss member or a rope or a cable, in which one length is much longer than the other two dimensions. So the other two dimensions, which are much shorter, are typically representing the cross-section. It's like cutting a banana across and seeing the circle and seeing the outer skin and seeing the core of the banana. So it's the cross-section of the banana. And from that we can see that there are two materials there. One is the soft shell, one is the outer skin, and then the properties of that can be calculated. For example, the cross-sectional area, the moment of inertia, and then from those we can calculate the stiffness when we multiply or combine the properties of the cross-section with the properties of the material. So cross-section behavior actually is composed of two parts: the geometric response or the geometric properties, and the material properties from which the cross-section is made. And when we combine them together, it becomes a cross-section. Otherwise, it's just a geometric shape. For example, if it's a rectangle, it's a rectangular shape with two dimensions. But if it is made from concrete, then it becomes a concrete cross-section, and the properties, for example, the stiffness, will then depend upon the moment of inertia of that shape multiplied by the stiffness of the elastic modulus of the concrete or the material. And this gives us the basis for determining the stiffness as well as later on the strength and ductility and capacity of this cross-section. So when we have a cross-section, you typically can calculate 7 types of properties of a cross-section corresponding to 7 degrees of freedom. And those are the axial deformation or axial degree of freedom along the member length. Those are the 2 shear degrees of freedom perpendicular to that along 2 axes. Those are the moment degrees of freedom or rotation degrees of freedom about the 2 axes representing the cross-section. And then you have the torsion and finally the warping. And each of these response depends on the properties, corresponding property. These properties, again, just like the material properties, are not constant, because they depend on basically the material property at that particular time or at particular strain. But for reinforced concrete, for example, it also depends on the level of cracking, amount of reinforcement in there, and the level of load. And for steel also, it depends on the shear lag and many other parameters, or the built-in stresses which may be caused due to the manufacturing process. So these cross-section properties are not as simple as they seem sometimes, especially when we want to do advanced analysis. Cross-section properties or cross-section response can be represented in terms of axial response. That means basically response to axial load and bending moments or 2 rotations. It could be the shear and torsion response, in which the shear stresses are involved corresponding to shear forces and twisting. Or it can be a complete general response in which everything interacts together. And ultimately, this response can be determined through testing, or it can be determined through computations. Computation of cross-section response is a topic of interest to many people, because it can lead to determining the capacity, it can lead to determining the deformation parameters such as the moment curvature curve, which is an interesting property in itself, and we will talk more about that in another topic. So what I would just like to conclude is that to understand structural response, we need to start with the understanding of the material response, and from there on we need to go on to understand the cross-section response to various degrees, like for example, axial only, tension compression, bending only, or axial and bending combined, which we may call axial flexural. So axial flexural response is critical to the design of columns, to the design of beams, and even to the shear walls. So we will go and move into determining most of these response in the following topic that you will see in the video. Thank you.